Hello, my name is Michael Brown. I'm a member of the faculty at the University of Washington in the Department of Earth and Space Sciences. We're located in the College of the Environment. This is the first video for a course on hydrogeology. This course is designed to meet the needs of advanced undergraduate and graduate students in the earth sciences and to prepare them for professional employment. The course also is appropriate for other graduate and undergraduate students in science and engineering fields. Module 1 consists of 5 videos. This video, a video giving a brief historical perspective on hydrogeology, substantive video on the hydrologic cycle, and 2 segments on current issues of sustainability. Are you ready? Let's start. So what is hydrogeology? Hydrogeology takes up from the point when water infiltrates the ground to the time it reemerges from the ground. It can reemerge in streams or other bodies of water. Hydrogeology involves an interrelationship between geologic materials and processes with the water contained within those materials. Hydrogeology has a descriptive component, but it is also a very quantitative science. And finally, hydrogeology lies at the intersection of natural resource issues and societal problems. So what is the intersection with society? Hydrogeology comes in with questions such as, can our aquifer support the development of yet another subdivision? Or, will the stream dry up and kill salmon if the farmer down the road doubles his irrigation pumping? Here's another example. Will my neighbor's septic system contaminate my well? Did chemicals leaking from that dry cleaning facility down the street travel through the aquifer, come to my well, and make me sick? Or, will water pumped out of the aquifer for the new salmon hatchery cause saltwater intrusion in my well? Hydrogeology also is a matter of global impact. Yeah, it's a simple question. How long can you go without water? Well, of course, not very long at all, just a matter of days. And what fraction of the world population does not have adequate access to water? Unfortunately, 13% are estimated not to have adequate drinking water, and more than 30% don't have adequate water for sanitation purposes. What fraction of the world population depends on groundwater for drinking, agriculture, and industry? Take a guess. Yep, it's 100%. Everybody in every country depends on groundwater in some fashion or another. So where is the groundwater being exploited? And by exploited, I mean being pumped out of the ground faster than it can be returned to the ground. The answer is nearly everywhere, unfortunately. So finally, will this have an impact on you, your family, our society? And the answer is certainly that impact will be felt increasingly within your lifetime. So what are the overarching goals in this course? Clearly, the most important thing is for you to develop an understanding of the science basis for groundwater management. As such, you'll be more informed and will be a better environmentally aware citizen. There are quantitative tools in this course, and mastering them will improve your skills that are more generally useful in a variety of science and technology settings. Finally, this is pre-professional training, and if you master this course, you'll know enough to pass the professional geologist licensing test in the state of Washington. And you should be able to gain employment in the field, leading eventually to hydrogeology certification. So let's talk about science basis for groundwater management. The course is highly quantitative. And let's bring into discussion a quote from William Thomson, better known as Lord Kelvin, the great 19th century physicist. He said, "I often say that when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever the matter may be." Hydrogeology has multiple professional applications. Clearly, there's the water resources we've already been talking about, contaminant transport. In civil engineering, a variety of geotechnical engineering and water control issues involve hydrogeology. Furthermore, waste management, both solid and radioactive, involves hydrogeology. Hydrogeology is quantitative and integrative. You will be using all that algebra, linear algebra, calculus, differential equations, partial differential equations that you had to take. You'll be using the physics, the energy, force, work, pressure, gravity, fluid flow, diffusion equation, Laplace's equation, chemistry, reactions, equilibrium, activities, acid bases, oxidations, the whole gamut of the basic science fields. And finally, geology. And in the following slides, I'll note that fluid flow is an essential component of almost every geologic process. These include pore pressure and deformation, faulting, dissolution transport, and structural geology. In seismology, there's an increasing recognition that fluids are part of the earthquake trigger mechanism. Magma processes involve fluids. Sedimentary processes include fluid flow. Geomorphic evolution is a process of fluids and their motion. Glaciology, geothermal, hydrothermal, geobiologic systems, and even extraterrestrial systems all involve hydrogeology. There are related fields. I'll have to mention heat flow. Heat flow shares much of the same fundamental mathematical theory, and the measurements of heat flow are very interconnected with hydrologic issues. Soil physics, that's the part of hydrology, geohydrology, that concentrates on unsaturated flow in the soil layers. Civil mining and engineering, you have slope stability, consolidation, tunnels and mine inflow of water. You have problems of dewatering, construction site, and various pore pressure geomechanic applications. In petroleum engineering, you have a similar conceptual underpinning. The main difference, though, in petroleum engineering is that instead of considering just water, you have to consider hydrocarbon fluids, gases, water, the whole gamut. Unfortunately, petroleum engineering introduces a number of opaque units which make communication between the fields less than ideal. I do have to mention a few limitations of this course. This is an introductory level course. It's not sufficiently comprehensive or detailed to make you a practicing hydrogeologist out of the box, but it will give you the fundamentals that will allow you to progress to that point. So what are you going to learn, and how much effort are you going to have in that learning? We're going to spend about 40% of the course talking about principles controlling flow of water in the ground, in the subsurface, and that's math, physics, geology. Principles controlling how water flows out at wells is about 10% of the course. Computer modeling will spend about 10% of the course. Chemistry of groundwater and transport of contaminants is about 20% of the course. The basic legal concepts controlling access to groundwater will spend about 10% on that. And then throughout the course, I will continue to bring in a discussion about sustainable use of groundwater and what factors are associated with evaluation of that sustainable use. Course resources. Well, of course, there are the lectures such as you're watching here. The website can be found through courses.washington.edu/ESS454. The text by Charles Fetter, Applied Hydrogeology, and let me hold up Here's what it looks like. There's the book. I will follow the book fairly closely, but I will use some fundamental and supplemental materials. My contact information is given at the bottom. I'm brown@ess.washington.edu. Course outline. I've divided the course into 10 modules. Each module is about one chapter, except we'll cover 2 chapters in the first module. The chapters are almost sequential in order with some jumping around. You can see that we'll go from the initial topics of history and elements of the hydrologic cycle to properties of aquifers, principles of groundwater flow, flow to wells, regional groundwater flow, geology of groundwater occurrences, groundwater modeling, chemistry of groundwater, quality and contaminant transport, and finally, groundwater law. My background. Well, I come into this having gotten a Bachelor of Science and Master of Science from the University of Washington. I traveled to Minnesota for my PhD, and I spent 4 years in Texas prior to returning to the faculty at University of Washington in 1984. My teaching portfolio includes everything from mineralogy, basic geology, to various kinds of geophysics, from exploration, gravity, magnetics, heat flow, seismology. I also teach some courses in the nature and context of science. My scholarly research involves planetary materials under extreme conditions. Currently, I'm measuring chemical properties of aqueous solutions and measuring elastic and thermal properties of minerals. I have been chair of geological sciences and geophysics and helped with the merger into the Department of Earth and Space Sciences. Let me give you a few pictures from my laboratory, where I like to think of it as extraterrestrial hydrogeology. I have a device that allows me to simulate temperature and pressure conditions found on the satellites of Jupiter and Saturn, Europa and Titan. And the issue with Europa is that it has an ocean that's almost 200 kilometers deep. The chemistry and the processes in that ocean are different than those found in the much shallower, lower pressure oceans on Earth. On Titan, we have a very unusual situation in which the rocky crust is, the rock is ice, water ice, and the fluids are methane and ethane. And this picture shows you a series of lakes stretched across the surface of Titan. Each of those lakes is probably mostly methane and ethane. The fact that these lakes are almost at the same elevation suggests that there are subsurface passages connecting them, so that there is hydrogeology on the planet of Titan. So, what are your responsibilities in this course? Clearly, start off, you read the book and the supplementary materials. You watch the lectures, you formulate and ask questions. You can complete the online quizzes, do the homework. Online material and instructions can be found through the website. There are 10 exercises, 10 exercise sets. Most are drawn from Fetter. I've supplemented with some additional assignments. There will be a final exam and a final report as well. I've designed this course to be about 100 hours of effort for an average student to get about an average grade. Now, clearly, average in this case is different from average in a lower division non-science course. I expect all of you taking this course are motivated, interested, and capable students. Therefore, the average grade in this class is likely to be high. 100 hours is an average. Many of my problems are open-ended, and depending on your interest and motivation, you may find yourself spending more time. With each module, I will give you an outline. For the first module, we have the course overview and what is hydrogeology. That's what you're watching right now. Following that will be a video on brief history, sustainability perspectives in the case of the Ogallala Aquifer, Then I'll spend some time on the hydrologic cycle, considering a variety of quantitative details and concepts. And finally, using the hydrologic cycle as the framework, I'll consider the Southern Nevada groundwater problem and what is the science basis for current decisions and ongoing controversy and litigation. With each module, I'll give you a list of vocabulary that I think may be new and different to you, or vocabulary that has specialized meaning within hydrogeology. When you review each module, you should review whether you understand all the details of each of these words. I also have put together learning objectives for every module, and mastering the vocabulary is always a module objective. Also, being able to identify and use appropriate units in calculation is a module objective every time. Here for Module 1, I want you to understand correct usage of significant figures in calculations. I want you to be familiar with the historical context of hydrogeology. You need to understand the hydrologic equation and all the basic components of the water budget, including precipitation, infiltration, runoff, evapotranspiration, recharge, discharge, base flow. You will need to understand that stream flow includes both runoff and groundwater discharge. You will be able to separate overland flow, interflow, and base flow components from a stream hydrograph, and you will be able to calculate annual recharge and discharge of aquifers using stream hydrographs. Finally, I hope you will be able to critically evaluate regional groundwater sustainability issues on the basis of water budget arguments, and you will become familiar with several examples of groundwater sustainability concerns. I want to give you a few notes on calculations. First of all, hydrogeology is a quantitative science, and that's quantitative even if the numbers are sometimes guesses. No apology, but I want you to be aware, units in hydrogeology are a nightmare. You will find a mixture of English, specialized United States Geologic Survey units, metric units, both non-standard international and SI units. Additional units creep in from the petroleum industry and engineering. You have to pay attention to units on every single calculation. An answer without the appropriate units given is going to be automatically graded wrong. 0 credit. No units, no credit. If a result of a calculation is a dimensionless number, you need to so state. Conversion factors will be your friend. I will give you several tables of conversion factors like this. You ought to keep them in a readily accessible place. It'll make your life much easier. Now, significant figures. You must be aware of significant figures. What do I mean by that? Well, an answer has no more significant figures than the least number contained in any of the input. An answer never increases in significant figures from units conversions or from use of irrational numbers like pi or e. An answer correctly derived and calculated will be graded wrong if it is given with an inappropriate number of significant figures. So let's talk about what an appropriate number of significant figures. If you introduced the following numbers into your hand calculator or into an Excel spreadsheet, 3.63491579 exponent 3 times 1.1 would give you 3.9984073 exponent 3. If you entered that on your answer sheet, it would be wrong. Notice that the input, one of the numbers only has 2 significant figures. Therefore, the answer has 2 significant figures. So the correct answer is 4.0 e to the third, or 4,000. Now I've put in parentheses there an additional bit of information. The number 1.1 could represent any number between 1.05 and 1.14. That's the round off. The round off is within a factor of 5%, so the final answer needs to lie within a range of 5%. So 0.2 is 5% of 4. So the multiplication indicated at the top line has an uncertainty of about plus or minus 200, indicated by the number in the parentheses. In Excel, always use the Format Cell dialog box to reduce significant figures to the correct number before you turn in your answer. This ends the first video, the course overview. Coming up next will be the brief history of hydrogeology. See you soon.